Hi everyone, I'm Corey Wolf, and today we're going to fine-tune Llama 3.1 on thousands of threat actor Telegram messages. So if you don't have a list of Telegram messages with sketchy stuff happening, you should probably go find some of those. It's not that hard to find. But once you do find those, what we're going to do today is we're going to grab all those messages. We're going to use them to fine-tune Llama 3.1, and then we're going to perform what is referred to as inference. So basically asking a question. So this is a little bit out of scope of what I normally do. So my day to day is OffSec, but it's important for me to, and if anyone in OffSec really, to keep up with threat intelligence because our jobs at the end of the day are to emulate threat actors, right? And so I am always interested in threat intelligence and finding ways to use threat intelligence so that I can do my job better. And so that's where this project started. I wanted to really just grab some threat intel, fine tune an LLM on it, and be able to ask it questions. So that's what we're going to do today. If we're going to look at it from a high level, when we think about it, it's really about first we need to gather data. We then need to create training data because we can't just take this raw data and fine tune, right? We need to format that data. We need to normalize that data and get it ready for fine tuning. So models use different formats. Llama 3.1 uses Alpaca, the Alpaca format, which is an instruction, an input, and an output. So at a very high level, this is what we're doing. We're gathering data, we're using that data to then create training data, and then we are fine tuning. For today, of course, we're going to use Telegram and the Telethon Python API. We are then going to take all that data, put it into the Alpaca format, and then using Unsloth today, these are just some examples you see on screen now, but using Unsloth today, we are going to fine-tune Llama 3.1. All the code that we're going to look at today is in a GitHub repo, which I have linked in the description. Also, if you want to cheat, you can use the data set that I gathered from this initial exercise. It is available on Hugging Face. I will also link to that. So, without further ado, let's get into it. Again, looking at all the code that's in the GitHub repo that's in the description, and thinking about our high-level process, it starts with gathering the data. So we're gathering data from Telegram, and Telegram, the API, for lack of a better term, is just kind of weird. It's weird. And so what we can do is we can use the Telegram API, and there's a couple of Python packages, but the one that seems most supported is Telethon. We can use a Telethon Python library to interact with the Telegram API. So that's what we're doing here. One thing that I would throw out is if you're not used to using Conda, the Python virtual environment manager, I highly suggest you do. I don't, for whatever reason, AI and ML engineers seem to love Conda. I tried with many other ones, pipenv, just regular v, env, and it just turned into a headache because one thing that we want to do is try and keep it simple. And so like everything that you see, like a lot of the tutorials call out Conda. So I would highly suggest that you learn how to use Conda. But the good news is that with Conda, we can still install all of our requirements with pip if we're just in the Conda virtual environment, which I think we are here. But we want to make sure that we're using Conda. The other thing that I want to call out is that I ended up using WSL on a Windows box. So I have a NVIDIA 4070 and setting up and managing NVIDIA drivers on Ubuntu in Mac is possible, don't get me wrong, but it's a huge pain. And when we do a lot of these things, it turns into a headache because you need to have specific CUDA versions, for example, and specific NVIDIA versions. This turned into a huge headache for me. And so what I ended up doing was just using WSL because it's a lot easier to manage all the drivers on Windows. And so, you can manage all your drivers, they will pass through WSL, and you won't have to worry about this stuff. That would be my second recommendation to you, right? And both these recommendations are really just about keeping it simple. There's lots of things that you're going to do or that you're going to see that just, it turns into a huge just configuration nightmare. So this is what I'm working with. WSL, a NVIDIA 4070 with 12 gig of RAM, and that's what we're doing. back to Telegram and using Telethon. So here you can see we're using the Telethon um, Python package. We're doing a whole bunch of stuff here. One thing to note is that Telegram has like kind of their own. It's like it's like OAuth-esque to where you do need to create an application with Telegram in order to do these things, and then authenticate with your Telegram user account to that app. So you will need to register an application, and you will get what's called an API ID and then an API hash. So I don't know if I said this or not, but the Telegram API is weird. It's just different. And everything, you know, with a lot of accounts, you're used to everything being based on an email address. With Telegram, it's a phone number. Side note, make sure you're performing good OPSEC, operational security. If you're going to be going into these Telegram channels and viewing them and poking around at them, use a burner number. Do not use, don't use your regular name. Just make sure that you're using good operational security because you don't want your information floating around. In my case, I do have a burner number that I use, yeah. So it all starts with the API ID, the API hash, and just Google Telegram register application. It'll come up. It's pretty easy to do. You just register it, and then you'll get these two values. Of course, you will need the phone number associated with it, as well as the username. So if we go down to where we're actually creating a Telegram client here, you can see that it's asking for the username, the API ID, and the API hash. So you do need a username in order to authenticate to the Telegram API. If you're looking through this code, you're probably going to see a whole bunch of stuff that's commented out here. This here is the function that performs that authentication. So it goes down, it says Telegram client, username, API ID, API hash. It'll start to perform, it's not OAuth, it's very similar to OAuth, but it'll start to perform the Telegram authentication where it'll ask you for your phone number. It will send a code to your Telegram account in the chat, so like it'll actually pop up. You have to enter that code, and then you enter your password. Once you do that, you will then be authenticated to the Telegram API using that application that you registered. You only have to do this once, because once you do that, it creates a session file, which I believe is just an SQLite database. Yeah, I mean, it looks like it. But once you do that once, and you're going to get this session file, and the Telethon Python library will always check and see if that session file is there. If so, you don't have to authenticate. That's your authentication. You're good to go. So this is commented out because you really have to do it once. Just don't delete the session file here, and you'll be fine. So that's why that's commented out. Looks like I did give one away here. So here's one Telegram channel. We'll get into that in just a second. So if we then went and authenticated, if we created our Telegram application, we authenticated and got our session file, we can now start to do some stuff. So we're all the way down at the bottom. Everything above here is really just functions, right? Everything above is functions, right? What's the main part of our application is here. It starts with client. So when our script runs, we create a Telegram client via the Telethon API. And then when we have that client, we use a loop and then run until complete. And it's going to run this main function, which is this guy here, right? So it's going to come through here. It's going to loop through our Telegram channels and perform the get messages function on it, and then dump it all to a file. So we create a client, we loop with that client on this function here, and this main function calls get messages on each channel that we have. So if you can see, there's a for loop here. If we go in and just actually look at the Telegram channels variable, it's actually a list. It's this here. So this is where you would put in your list of Telegram channels. And the easiest way to do this is to get the share URL, which you can find in Telegram when you go to the info section of that channel you're in. This is where you list all the channels that you want to get messages from. So this is a starting point. So in that for loop that we saw before, it's just looping through each Telegram channel and then running this get messages function on each individual channel. We'll step through this in a second, but a couple things that I want to call out. Again, this is all in the GitHub repo, so you should be following along with me. You should have the code locally, but yeah. So a couple variables here, max messages per channel. We want to limit the number of messages that we pull per channel. Max total messages, so we want to limit the number of total messages that we gather. We then define an empty list called all messages, which of course is going to hold all of our messages that we get. And then another empty list called channel messages, which as we loop through and get all the messages from each individual channel, this is going to be the list that holds the messages for that channel. There's a couple different reasons for that, which we'll get into in a minute. This file name here is just what you want the messages to, the file name of the messages the file name that you want to save the messages to. There we go, got it out. Which you can set this here to whatever you want. I have it set to Telegram messages. So all this stuff here is simply for connecting to the API via our app that we registered. These variables here are for limiting the number of messages and basically counting the number of messages that we have in each channel and then how many messages we have total. This file name is literally just the name of the file name that we're going to write all the messages to. And then of course, Telegram channels, which is a list of share URLs for each channel that we want to get messages from. So if we go back to our main, right, we're creating a client, we're looping through it, and in this main function, we're doing client start. So we're actually starting the client. This is part of Telethon and Telegram's API requirements. We're looping through all our channels, and then we're calling get messages on each single one of those channels. And then finally, we're opening our file name, and we're dumping all those messages into a file, named file name, whatever we call it. So let's take a quick look here at this get messages function, which is really kind of the main part of what's happening here. Let's see if we can do a little word wrap so it's easier. That didn't really help that much, but if we go, we can look. So remember, this get messages function is called every time we loop through a channel. Telegram refers to so an entity in Telegram could be a channel, it could be a group, it could be a super group, it could be a user, right? And what we can do is we can actually see channel equals await client.get entity. This get entity function method really takes either a share URL or a peer ID. So you can get a peer ID via the Telethon library, but it's just much easier for our purposes to literally pass this share URL like we were talking about just a few minutes ago. So we're passing that entity, which is a share URL, to this function. So if you remember, channel messages holds all the messages that we are currently gathering from a specific channel. So remember, this is a loop now. So if we're in the second iteration of this loop, we want to empty this because that means that we've moved on to another channel. So in this function, we're just clearing out that list just to make sure that there's nothing left over from another iteration of the loop. We're calling our client to get entity, which is our channel, right? And so we're assigning that to channel. One thing to note is that everything is async await. It basically just means that the script is going to wait until this method completes before it moves on. Async await is kind of beyond the discussion for today. Lots of good videos out there but it basically just means that we're going to wait. The script is going to wait for this to happen before it moves on, right? Then what we're doing is we're looping through. And so we're saying while. So remember, all messages is the list that contains every single message from all channels. So we want to get the length of that. And we're saying while the length of all messages is less than the max total messages, right? So this is limiting how many total messages we get. And then the length of channel messages, which is per channel, basically the messages per channel, as long as that length is less than the max messages per channel, let continue. And so we're using our client again here to use the method getHistoryRequest. And the two big things that we want to point out here, well, I guess maybe the one, there's some other things, but we're saying the peer is the channel, which we got above, right? So we got up here. The channel is client.getEntity, and we're passing that entity into the peer field for this. And we're basically looping through, right? We're looping through. I mentioned before that the Telegram API is kind of weird. It absolutely 100% is weird. And so one thing that I did want to call out here is, so we call history. So we get a history request, which basically returns back messages for us. And then down here, we're saying, all right, messages equals history, because we get a history request object back. And in that history request object is a messages field. So here we're saying, hey, if there's no messages in the history request object, break out of the loop. If there are, assign that field to the variable messages. So all of our message, now remember, these are message objects, not actual strings. These are message objects. So this is a list of message objects. And then we're just converting the channel title to string. And we're looping through all those messages. So remember, this loop right here is a list of message objects. A message object could have lots of different attributes or fields. One of those being date, right? So our message object has a date field, which of course tells us the date that the message was sent. It also has a message field, which is the actual message that was sent. You can see that we're doing an if statement here to say, hey, if there's a message field in the message object, continue. We're checking for that because the Telegram API could return a message object that doesn't have a message. So it could be a file attachment, for example. So that message field might not have anything in it. So we're checking, like through each one, as we go through all these message objects, we're checking to make sure that there is actually a message. There is something in the message field of that message object. And if there is, then we're continuing. And so this is where we're actually starting to build the message that we're going to save. So one thing I do want to call out is here where this will return all kinds of random stuff. So there's emojis in this. There could be emojis in this message. There could be all kinds of random encoded characters and random stuff that could be in this message. So one way to kind of strip everything down, because remember, this message is going to go into training data, right? And we want to just make sure that we have ASCII text. And so one way that you can remove everything except for ASCII from a string is by encoding it, and of course ignoring the errors, and then decoding it, which will return a string of only ASCII. So this is why we do this, right? Because we just want to strip everything out except for ASCII. Our actual message, we're going to add some context for later because it's going to be used in fine-tuning. So we want to add some context to our message, and you can see here that's what we're doing. So we're saying on message date, in the Telegram channel named channel title, the following message was sent. And then we're adding a new line and then the actual message. Again, we're doing this for context because later what we're going to do is we're going to generate Q&A pairs to use for training. When we think about that training data part, one way to create that training data is by creating Q&A pairs. And so we're going to do that. We're going to create Q&A pairs. So that's why we're adding this context here. Now remember, we're saving these to a text file. We want every message to be on a single line. And remember, these messages could have multiple lines. It could have bullets. They could have numbered lists. It could have all kinds of random stuff. And so for me, I thought it was easiest to just simply take this whole thing, this whole line. And now remember, this could have, who knows what the message actually is, right? It could be all kinds of different stuff. Bulleted list, whatever, numbered list, whatever. For storage, it was easiest for me at least to just take this line, base64 encode it, and then actually write it to our list of messages. So that's what we're doing here. We're writing our list of messages. So channel messages has a list of all the messages from the channel. All messages has a list of every single message that we gathered between all channels. And these are basically just lists of base64 encoded strings. This one. So that's what's happening here. It's looping through every single channel, aka entity, as Telegram refers to them. It's looping through there. It's gathering messages up to the max total messages and max total messages per channel. It's doing some cleanup here, right? It's doing some cleanup. It's adding some context here. Then it's base64 encoding it and adding it to our Python lists. So we go through, we do that for all of our channels. And at the end of the day, we are left with this list, all messages, that has all of our messages, one per line, base64 encoded. If we go back to our main function, we will see this is where we are writing it. So for line in all messages, file write, and that's where we're writing it. Again, in the GitHub repo, in the description, all this code is there. Ideally, you're following along. So let's try this out. And let's I'm going to have to add these back, I think. You should really be doing your own research, but you might get a freebie here. Oh boy, you gotta watch me muddle through this here. There we go. All right. Maybe you got some free ones, maybe not. But what we can do now is we can run it, Python. And now you should have installed all of the requirements by now. So there's a requirements.txt in the GitHub repo. You should have done that by now. And so now it's going to connect and it's going to run through all these chats, all these channels, and gather all the messages. So this is going to take a minute, and we'll come back when it's done. All right, so we're all done. You can see that total messages obtained was 18,567. And so we should have a file now. Telegram messages. Yep. So you can see they're all base64 encoded. This is 18. I'm gonna miss a scroll, aren't I? I'm gonna miss a scroll. Oh, there we go. 18,567, right? All base64 encoded. Let's grab one and just kind of see what kind of nonsense it is. And we can do this. So here's one of the messages that we gathered. And you can see on this date in the Telegram channel named Star Chat, the following message was sent. And you can see this message. So this is why base64 encoded it. So you can, of course, like flatten it and then do new line characters and all that kinds of stuff. I wanted to try and keep the message as the same as much as possible. So that's why base64 encoded it. But we have 18,500 something of these, right? And so now what we can do is we can take all these messages, and now Llama 3.1 is an instruct model. One of the best ways to fine tune an instruct model is to create Q&A pairs. So you give it a question and then you give it the answer. If there were just, I don't know, if there were just 20 of them, that'd be fine, but we have 18,000 of them, right? And so this is a lot. It's a lot to take in. And we need to now take these 18,500 messages and create Q&A pairs for them. Now what we can do is we can use Ollama, and Ollama allows us to run models locally. So we can pull models down. It has a command line interface, also has an API. There's lots of different formats that like models can come in, but Ollama requires a GGUF, which is a GPT generated unified format. Excuse me. It uses Llama CPP under the hood. Just Google Llama CPP. You can figure it out. But basically what we can do is we can use Ollama to spin up another model and tell this model to create questions for answers. And our answers are the messages, right? So we can send an answer, aka a message, and say, okay, in this case, I went with NeuroChat, which gave me the best results. Tried a couple different ones. NeuroChat ended up being the best one. Just worked out the best, at least. So we can say, all right, here's a message, aka an answer. Generate a question for it. So that's what we're going to do next. If again, on GitHub in the repo, you should be following along with the code. We're going to look at generate Q&A pairs. One last thing to think about, and I mentioned this earlier, is that different models use different formats for taking in data. Llama 3.1 uses the alpaca format. And so that consists of an instruction, an input, and an output. So when we generate these QA pairs, we want to then create our questions and answers in the alpaca format. So that's what we're going to do. So if we look at generate QA pairs here, we can actually see, let's get some word wrap here for you again. We can actually see what we're doing, right? So we are using the API from Ollama. Actually, let's look at Ollama quick. So Ollama is really easy to install. Just go to the GitHub repo, you'll see it. But Ollama has a lot, not lots, but a couple of different commands that you can run. I called one out before, pull. So if you go on the Ollama website, there's a whole list of models that you can just pull right from their repository. You can also create your own and import them, which is what we're going to do. But like, for example, if we do Ollama list, you'll see all of the models that I have installed on my local machine. I have a decent amount of them here. These are the ones, that we've been working through, that I've been working through, really. And like I mentioned before, we're going to go with NeuroChat, this one here. But we can pull down any from the Ollama repository. We can also create what's called a model file, which we will do later, and import our own local models. And Ollama is super useful. Not only can you use it to pull models, but you can use it. It has an API that's running, so we can call local hosts, and call an API to get a response. But you can also do CLI. So if we do Ollama run NeuroChat, what it's going to do is it's going to spin it up locally for us, so then we can actually just perform inference right here through the command line. NeuroChat, don't have it loaded right now, so it's taking a minute. There we go. But now we can ask it questions, like what is a llama? And it's pretty quick. NeuroChat's good, and it gives the kind of responses that we're looking for. It does it fairly quickly. So NeuroChat's the one that we're going to go with. We're going to use Ollama, not from the CLI, but via the API that it serves up on localhost. So if you have generate QA pairs open, this is what we're looking at. This is the messages file name from before, so this is the one that has the base64 encoded messages. This is just a variable for what we want to call our file once we get the response back and we dump all the responses back in alpaca format. We need to store those in a file, a JSON L file. It stands for JSON lines. Basically just means that there's a JSON object per line. This is the model that we want to use. So we talked about NeuroChat and the API location, which is on localhost. And this is the URL, or this is the endpoint that we want to call on the Llama instance. And so we can just use regular Python requests to make a request. And that's what we're doing here. We're setting a user prompt, right? Which we say, act as an AI engineer and generate an input from this chat message to be used in fine-tuning an LLM. Your response should be succinct. Your response should only include one corresponding question and nothing else. So we do this because I'm sure we've all interacted with ChatGPT or any one of them. They always say, sure, I can answer that for you, and then they actually give you the answer. We don't want that. We just want straight up question, right? Just give me the question, because we're going to take that response and dump it into an alpaca format file, right? And so this is our user prompt, and this is our data, our post data that we're going to send in our API request. This is the variable for our model, which is NeuroChat. These are options specific to LLM. So temperature is basically how in-depth the model response is. And these, I don't know. Great. Well, I know number of context tokens. That's basically the number of tokens that the LLM will take when it's generating a response. If this was super low, it would only take like a certain portion of the message. So it's fairly high context. I mean, for a local model, it is. Top K, no idea. Go look in Ollama. It has to do with something with how creative the responses are, how conservative it is, and its creativity, all this other kind of stuff. Whatever. And then our system prompt. So you are a master at generating inputs for fine-tuning large language models. You are provided a chat message, and your job is to generate an input for that chat message. You must obey the following rules at all times. 1. You must reply with only your provided input. Do not say anything before your response, and do not provide any supporting information. 2. Your responses must be applicable to the input field of a data set using the alpaca format. And so this is literally our post body, right? And further down the script here, we're basically just looping through this get instruction function and calling it for each message, which we refer to as output in this function. And we're just sending the post request and getting that response back. So if we go down, we have an empty list to hold our data. So this is what we're going to dump to our JSON-L file, this one here, right? So we have an empty list. We open our Telegram messages.txt file. We loop through, and this is where we're looping through each line. And it's just some fancy stuff to show a progress bar. But we're looping through. We're base64 decoding the line. We are doing another ASCII, right? And then we're doing an instruction. So we're going to that function that we showed above, which is actually making the post request. And this is returning, so if we go back, return D response. So this is returning the actual response from the LLM. The Ollama API will return back a bunch of other data as far as time to run, all that kind of stuff, number of tokens, all kinds of different stuff. All we want is the response in this case, and that's what this function is returning. So we're looping through each line. We're calling this. We're saying perform the function to ask the LLM to generate a question for this message, aka answer. And then we're appending another line to our data list that's in the alpaca format. And we're just looping through all the lines. We're just doing that. So in this case, we're going to make 18,500 calls to our NeuroChat model that is running via Ollama API. last time I did this, it took 4 hours. It took 4 hours, so just keep that in mind. On a RTX 4070, 12 gig RAM, took 4 hours to do the 18,000. So that's all we're doing. This is our main main portion of our file, creating an empty list, looping through the file. Each line, we're calling this get instruction function, which calls NeuroChat via Ollama, and then appending that response to our data list that is in alpaca format, and dumping it all to a JSON-L file. So if we go, we can go here, let's clear this out. We can now do it. We can actually do Python generate QA pairs, and it's going to start to run. So again, last time I said this took 4 hours. We're gonna wait. We'll come back when this is done. All right, so I didn't feel like waiting this long, so I've already done this. I was gonna wait, but I'm not gonna do it anymore. What you can see here on the left are some examples of what the questions were that we received back. What were the requirements and expectations mentioned in the Star Chat Telegram message? What was the content of the message? What is the offer and services provided by the Star Chat Telegram channel? What percentage of their earnings do they share with their clients? So these Q&A pairs are decent. There's lots we could do to refine this and maybe get better ones, but these aren't half bad. And so these are just some examples of what we got back. If we go, and I can actually pull up Q&A pairs, right? Here's some examples of all of our Q&A pairs. You can see there's just tons of them. So what was the nature of the work you did for Beat in the Jacuzzi Telegram channel? All right, that's pretty good. What are possible concerns? North Korean hackers and their involvement with cryptocurrencies. So we got some decent questions in here. Overall, I think the data set's pretty good. Of course, it could always be cleaned up, but you can see these are now in that alpaca format in JSON-L, which means that there's one JSON object per line, and our output is the messages that we got, right? So now we actually have gathered all the messages. We have we have gathered all the messages. We have created the Q&A pairs using NeuroChat. And if we go back, and now we are at the point where we can fine tune. I mentioned earlier we're going to use Unsloth. Unsloth is a library that's used to fine tune models. And I don't know how exactly, but they found a way to reduce the required RAM and memory needed and resources needed just in general. Excuse me. And so Unsloth's pretty popular library, I guess, that you can use to fine tune. So again, this is all in the GitHub repo, which you should be following along with the code. But we can actually go to train now. And so you can see in one of my comments here, most of it is taken from actually a Unsloth tutorial. Unsloth has lots of good examples. And so a lot of this was just taken straight from there with a couple of tweaks. Unsloth has good code for tutorials. There's good videos on Unsloth. They make it extremely easy to fine tune models, right? And there's a couple different ways to fine tune models, but one that we're going to use is we are going to create what are known as LoRa adapters. So this is a low rank adaptation, and it's a common method for fine tuning models. Basically what it does is it freezes all the weights of the original model, in this case Llama 3.1, and then adds an additional layer on top with our data of different weights, right? New weights, I guess, but it adds our data on top. When you do this, LoRa adapters are kind of a separate thing, and by default they're saved on their own, just the adapters. So it's not like you can take the LoRa adapters and perform inference on them. You need to merge the LoRa adapters with the base model, Llama 3.1 in this case. So if we go back and look at our train.py, you can see this is what we're doing here. And if we look at kind of the process with Unsloth, we want to fine tune. I mentioned earlier, there's different ways that models are saved. One of those is a GGUF. That's what we want because we want to be able to take that GGUF and use it in Ollama. So if we look at kind of our process for fine tuning with Unsloth, we fine tune, we get our GGUF, and then we use that to import it into Ollama. If we go back to our code, most of this, again, like I mentioned, is just taken from a tutorial. The model name, so Unsloth has, you can download Llama 3.1 directly from Unsloth. So here what we're doing is we're saying load the tokenizer in the model using fast language model. So this is from Unsloth, right? Fast language model. And basically load it up. So if we do fast language model.from pre-trained, it's going to load Llama 3.1. It's going to set some variables, which we have up here, and that's going to return the model and the tokenizer. And basically that's what we're doing here, right? A couple other things. Normally, where is it? Where are we? Data set. So if we go here, where's our data set? Scroll down. There we go. So our data set, this is through Hugging Face. And so in this case, we're doing load data set and we're loading a local file. This is how, if you were to just put in a Hugging Face data set in here, it would pull it down from Hugging Face for you. And it will just load that for you. Like, so you can use data sets that are stored in Hugging Face to fine tune. But in this case, we are loading our local one, which is in that file name. It's then mapping, it's taking all those entries and making sure that they are in alpaca format. And so now we have our data set here. And we're loading that in. This is just a function, right? Up here is our prompt, which will be used to format. This is more stuff with the model. Again, read Unsloth for that. Down here is where we're actually training. And so all these are hyperparameters. So when you train, there's all kinds of different things that you can do. But one of the things I'll call out is number of epochs. So an epoch is how many times each row of data is actually used for fine tuning. So if this was set to like 0.5 or something, like if this was 0.5, that means that only half of our data would actually be used in the fine tuning. And for me, when I was doing this, I did this 3 times. I did 3 epochs. So that means that the training went through 3 times. It went through the data set 3 times. Max steps just limits the number of steps, which is basically rows that training intervals, which again, if you have 18,000 rows, well then that's going to be 18,000 steps basically. But if you set epochs here, it's definitely going to run through the whole data set at least 3 times. I'm not going to try and go through this because I don't know, Google it. A lot of stuff going on there. And it's as easy as now just saying trainer.train. And this is a Hugging Face thing, this trainer. That's it. So it'll load our data set. It'll set some parameters for fine tuning like epoch and max steps and that kind of thing. And it will then train. Now, Unsloth has, if you were to look at their documentation, they have a function which is model save pre-trained GGUF and the name of it. That's not going to work, at least at the time that I'm recording this video. This did not work. It required all kinds of random stuff from llama.cpp. It's kind of wonky the way that Unsloth implemented it. Didn't work. So what we ended up doing is saving the pre-trained merge. So if you remember, I said LoRa adapters are saved separately. And so what we're doing here is we're saying merge the LoRa adapters with the underlying model, base model, Llama 3.1, and save it. So that's what we're doing. And so we're saving it in a merged 16-bit format. What you'll get once this is done, let's actually, let's see. So if we do train.py, you'll see it's actually going to start running through, and it'll spit out stats as it's doing it. And so you can see Unsloth's doing his thing. If this was the first time we were pulling down Llama 3.1, you would see it download Llama 3.1. So now you can't hear it, I can, but my machine is revving up because it's getting ready to train. And so you can see it's now actually training for those number of steps. So one thing I do want to clarify about steps is that you can set a batch size. So per device train batch size. So I only have one device. So that means it's going to do 1,150 steps of 8 each. So, I don't know, what's that? Yeah, I should know. I should be able to do this. Oh boy, we got too much here. So 1150 times 8, 9,200. 9,200. I'm sorry. Let's back up. We have our batch size of 8, and then gradient accumulation steps. So that's 16. So that basically means that for each step, it's going to do 16 of these. So if we go and look at calculator now and do 1150 times 16, 18,400. So that means that it should hit pretty much every message or row of training data. It should hit every single one of those. We're going to miss 100, right? But it's going to go through and hit every single one. And because we set it for 3 epochs, it's now going to do that 18,400 times 3. So that means that we'll get through the bulk of every single message at least 3 times and train the model on it at least 3 times. Let's go back and look at, yep, you can see we have loss, which we want to see over time, loss going down, trend down. You can see it's on epoch 0.03. This will take a decent amount of time. Let's look at system utilization real quick. Yeah, you can see GPU is spiking up. It's spiking up so much that this thing's a little laggy. But you can see it's working, right? It's doing work. Dedicated GPU memory, 8 gigs out of 12 is being used. Looks like 21 gigs. So my machine is a 12-core Ryzen 5950, 64 gig of RAM, SSD. I think it's a terabyte if I remember correctly. But yeah, so 22 gigs of RAM is being used right now. The GPU is maxing out here and there. So we will let this run, and when it's done, I'm going to stop it. But when it's done, you'll see that we have. So I mentioned before that there's different formats in which models are stored. One of the base formats is called safe tensors. So if we look at our output, because this, when you're doing this, you're basically telling it the output folder. And so it puts all that in this folder, and you can see that there's safe tensor files, which they're binary files, so it's not going to do anything. And then there's just different config information related to the model itself. So this is what we ended up with. We ended up with these sets of files, which if we wanted to, and we had an application that supports it, or if we built a Python script ourselves, we could perform inference on this. This model is good to go. But remember, we want to use it for Ollama. And so with Ollama, what we need to do is create what's called a model file. So let's clear this, right? Well, first, let's back up. we have to create that gguf. So I mentioned llama.ccp, and one of those, one of the functions that comes with that, what happened here? Oh, there we go. So you can just clone the llama CCP repo, and if you look at it, there's a whole bunch of stuff here, but you can see there's some helper scripts. So what we can do is, because of llama CCP, we can just convert it now. So we can do convert Hugging Face to gguf, and then what we do is we pass it the folder, so this output folder that we set here, which is, in this case, it's up here. What am I doing? Oh, missed that. And then one of them, whatever. Telegram 1150 steps. Uh-oh. What is that thing called? Telegram 1150. Oh god. This is what happens when you demo stuff. 1150 steps. There we go. Got it. And then we set an out file. And you just set that out file to whatever you want. So, you know, your model name .gguf, right? And you also want to set the out type to F16. And so if I was to run this, we would get a single file, gguf file, that we can then use. So let's go back to that main folder and look at the files in there. And so you can see I have a couple of them in here. ggufs. They're big boys. Look at them. They're big boys. They're not small. A couple gigs. And so we have that single file. So we took the folder that contained all those safe tensors files, and we took them, and using llama CPP, we converted it to one single file, a gguf file. So now we can take that and put it into Ollama. And so what we need to do is create a llama or a model file. Now I have a couple of these, and we'll just grab one, 1150, and cat it out. It's as simple as just saying from, and then put the path to your file. That's it. And then what you can do is you can go into Ollama and you say create. Well, let's actually look at the help. Oop, that's not right. Oh, I screwed it up all the way. Not just a little bit. Ollama, create, and actually look at the help. So we can say create the name of the model. So, and then dash F and the location of that model file that you created. So in my case, it would be Ollama create Fenrir again, whatever I want to call it, dash F, and then the location to this model file. Once we do that, it will do a whole bunch of stuff, and then we can actually run it. So just to kind of recap what that is, we can now actually run this locally. And so let's do that. So in this case, we can do Ollama run Fenrir. I forget what it's called. Ollama list. Yeah, this is the one we want here. So we can do this. Ollama run. Run this one. So now it's going to load our file, the one that we fine-tuned, and it's going to run it, and we can actually perform inference on it, and we can ask it all kinds of questions. So there's different things that we can do that'll make it better or worse. The real thing about when you fine-tune is trying to change all those hyperparameters, making sure that your data is of the highest quality, and going from there. Because all these little things, there's lots of different variables that, depending on how it goes, it may or may not work, right? So here we can ask one. Let's ask a question. Oh boy, here we go. What is the main feature of each service offered by Gorilla Panel? So this is one service that was advertised in one of the Telegram channels. Sorry, excuse me. And we'll see that it's going to spit out a response based on that data that we gathered. And this is true. It provides users with different options. Oh, let's look at resources again. You can see the GPU is starting to put in some work. And oddly enough, it's taking more memory. So it's using 11 gigs out of 12 of GPU memory to run it, as opposed to when we fine-tuned it, which is kind of interesting, right? So this is working. It's going on. We can change different parameters in Ollama, like model parameters, to say, only so much tokens in a response, etc. It's going to keep going on in this case. But now we have a working model that we fine-tuned on data. Next steps, refine the hyperparameters such as learning rate, number of epochs, number of steps, get better data, get more data so that we can go and get even better results, right? But this is what we have. So we can actually now query this model and ask it about sketchy stuff. I guess you could consider it uncensored. It's going on quite long right now, which means that I should change the context length. I've been talking now for a minute or so, and it's still typing stuff out. My GPU is maxing out. But the fact of the matter is that it works, and it's giving the right, it's summarizing. It is giving correct information. This information isn't wrong. I double checked it. This information isn't wrong. It's just we want to fine tune how it gives us our responses back, which is what we can do when you set context length, you set temperature, all those things that we talked about a little bit ago. We can customize how it actually responds. So it works. Yeah, there we go. There we go. It's all done. We got it. Yeah, I think that's it for today. Excuse me. I think that's it for today. I hope this was helpful. Again, all this code is in the GitHub repo, which is linked in the description. All the data that I gathered during the original run of this project is available on Hugging Face. I'll put that in the description as well. I hope this was helpful. I hope you can find a way to fine-tune what we did here today and make it better. I would love to hear from you if you do.